In this module, we turn requirements into a working architecture. You'll connect the Besu network, smart contracts, enterprise applications, and operations into one design, with decisions that support security, integration, monitoring, and production readiness. So far, you've built the foundation: Besu models, node architecture, consensus, permissioning, smart contracts, governance, security, and operations. From here, we shift from understanding requirements to making architecture choices. So the private Besu network we deploy next is purposeful and production-minded. Good architecture starts before any node is selected. For Besu, the key question is what the network must optimize for: trust between parties, auditability, privacy, speed, uptime, compliance, or ease of operations. These goals can compete, so architects need clear decision drivers. Use the requirements captured earlier to define throughput, latency, availability, recovery expectations, governance boundaries, and regulatory constraints. Once those drivers are explicit, design choices become traceable instead of opinion-based. Think of the Besu network as a set of organizational domains, not one shared server. Each member operates its own nodes, while validator duties stay protected from public RPC traffic and routine administration. Shared services help participants find peers, enforce permissioning, and observe network health. Transactions enter through controlled access points, propagate to validators, and become final blocks. The design should also make it straightforward to onboard new participants without redesigning the network. A strong Besu network separates responsibilities instead of making every node do everything. Validators are the most sensitive because they participate in consensus, so they need hardened access, monitoring, and high availability. Member nodes give organizations their own view of state without necessarily producing blocks. RPC nodes serve as the controlled front door for applications and APIs. Bootnodes support peer discovery. Treat each role as a boundary that reduces blast radius and makes operations clearer. Validator design is where the trust model becomes operational. IBFT 2.0 and QBFT both provide fast finality, but the right choice depends on governance, performance, and team maturity. Often, the bigger risk is not the algorithm itself. It is concentration of control. Validators should be distributed across organizations, regions, and operating teams. Also define how validators are added, removed, rotated, and recovered during incidents. Quorum rules determine how many failures the network can tolerate before consensus stops. Permissioning is the control plane for an enterprise Besu network. First, decide which nodes are allowed to connect and participate. Then define which accounts can submit transactions. These rules should not be ad hoc. They should map to onboarding, governance approvals, compliance checks, and revocation procedures. Strong designs use layers: network access, node access, API access, identity controls, and contract-level roles. If one layer fails, the next still limits what an actor can do. In a consortium network, every participant needs a clearly defined infrastructure boundary. Each organization should know which node it runs, how RPC access is exposed, where keys are protected, and how logs and metrics are collected. Hosting may vary across on-premises, public cloud, or hybrid environments, but the deployment pattern should stay consistent. Ownership must also be explicit for maintenance, backups, upgrades, and incident response, so shared governance does not become shared confusion. Production networks need observability built in from day one. Each Besu node should expose health signals such as peer count, block height, validator status, transaction pool size, CPU, memory, and disk usage. Metrics and logs flow into shared tooling such as Prometheus, Grafana, and Alert Manager. The goal is early detection. Downtime, forks, peer loss, latency, or disk pressure should trigger clear alerts before they become governance or service-impacting incidents. Start contract design by translating the business domain into contract concepts: participants, assets, agreements, approvals, and lifecycle states. Then decide what truly needs shared verification. Rules, permissions, and state changes usually belong on-chain because every party must trust the result. Private data, large files, and high-volume records often stay off-chain, referenced through secure interfaces. Strong architectures make each transition explicit, authorized, and modular, so contracts remain understandable, auditable, and easier to evolve. A smart contract should make responsibilities and transitions explicit. Roles define which participant can create, approve, audit, or operate a record. State variables capture only what the contract needs to enforce rules, such as ownership, status, balances, and key business data. As actions occur, events announce changes to integration services. The lifecycle becomes predictable. Deploy the contract, process active transactions, review approvals or exceptions, and complete the record with a clear audit trail. A smart contract upgrade strategy is really a risk strategy. Immutable contracts maximize trust and audit clarity, but defects may require workarounds or redeployment. Upgradable patterns offer flexibility, yet they add powerful admin controls that must be governed, tested, and monitored. Versioned redeployment keeps history clean, but requires migration planning and participant coordination. In enterprise systems, choose the pattern before launch, document permissions and migration logic, and tie every change to formal approval processes. Applications should not talk to Besu as raw blockchain clients. Put a service layer in between. The API exposes business actions, such as creating an asset or checking audit history, while backend services handle identity, permissions, signing, nonce management, retries, and event processing. This keeps the user experience predictable and protects RPC endpoints behind gateways, authentication, authorization, and rate limits. The result is cleaner integration, safer operations, and less blockchain complexity leaking into the application. Enterprise Besu networks become useful when they fit into existing IT. Identity systems authenticate users before applications submit transactions. Smart contracts emit events, and listeners turn those events into updates for ERP, CRM, reporting, or compliance tools. Off-chain databases store searchable views and private metadata, so teams are not querying the chain for every dashboard. The key design principle is separation. Keep trusted state on-chain and use surrounding systems for access, workflow, analytics, and operations. You now have an architecture blueprint. Network roles are separated. Contracts define state, events, permissions, and upgrades. Applications connect through APIs, identity, off-chain data, and enterprise systems. Next, we turn that design into a working private Besu network, then integrate and harden it for production.